Welcome. This is a brief introduction to statistical analysis. We will begin with historic data taken from diabetes research to illustrate some of the fundamental ideas of applying probability theory to data analysis. Next, we will work through a couple of statistical tests using Excel and interpret the results. And finally, we will point to resources that can be used for more complex and comprehensive analysis. Early studies of diabetes investigated genetic inheritance of the disease. Namely, can abnormalities in carbohydrate metabolism be detected in children of parents with type 2 diabetes? Fasting blood glucose levels are measured in 25 children of parents with type 2 diabetes and 25 control children. Here is the data. The question is there a difference between these two data sets? Summary statistics were taken, namely the mean and standard deviation of each group was computed. Each data set was graphed to get a better picture of the distribution of the data. Box plot. The question is, these small observed differences, is there some underlying force that's causing them, or are these small differences due to natural variation and chance? What accounts for these observed differences? Are these two groups truly different? Or are we simply seeing the natural variation of a single group? All populations are variable. Data sets drawn from a single population will contain a certain amount of variability. Data sets drawn from two different populations will contain a certain amount of variability. Statistical tests give us the tools to tell the difference between the two. Descriptive statistics and graphs may strengthen our intuition on a situation, but they are not sufficient evidence to make conclusions. It is more scientifically rigorous to state that observed events occur with given probabilities. Then, set within a stochastic framework, one can say that decisions are made if events fall beyond a set probability level. A few standard statistical tests to determine the difference between means in a single factor design are the t-test and the ANOVA, and then the follow-up post hoc test. These tests are used when the data is normally distributed or follows a Gaussian curve. The data generally is bell-shaped and symmetrical about the mean. To use these tests, first we set up hypotheses. The null hypothesis, H0, states there is no difference between the means in these two sets. The alternative hypothesis, H1, states there is a difference between the means. This is the t-distribution. We'll use this as an example to describe some of these concepts. The t-distribution is a probability distribution. The horizontal axis is an axis that describes the independent variable measurements. The vertical axis, the height of the curve, is the corresponding probability for each one of those events. Events that occur in the middle here are more likely than events that occur in the extreme ends. Alpha is the level of significance used to make judgments. It's typically set at 5%. This is the probability level that one uses to make decisions whether data sets are different from one another. This picture is describing a classic two-tailed test. The fact that it's a two-tailed test comes from the alternative hypothesis, H1, which simply states that there is a difference between the means. It doesn't say that the difference is greater than or less than, just there is some difference. So you would account for that by saying, well, possibly the test sample, its mean might be larger than or might be smaller than the reference mean. So therefore, we take this alpha level, 5%, and we break it in half, and we put half of that in the left tail and half of that in the right tail. You can notice that this curve is composed into three regions. Reject HO is this left tail, known as the critical region. Do not reject HO in the center, and then another reject HO in the right tail. In order to use this curve, one must calculate a test statistic from the data. That test statistic can be calculated according to this formula. I will describe it pictorially here, but in reality, we would use a software application and you wouldn't be crunching these numbers. Regardless, looking at the data, one would use this formula and calculate the test statistic. In this case here, our test statistic from the data from the diabetic children example came to 8.33. On this horizontal axis, 8.33 falls in this very extreme tail, which is in this critical region. It is very unlikely that this observation would occur by chance. Also, we have the p-value, which is the area underneath the curve that falls between the test statistic and the extreme end of the tail. This p-value is the accepted level of uncertainty that researchers use where they would reject a null hypothesis that is otherwise true. In our case here, being that our test statistic falls in this critical region, in this extreme end, that states that we have enough evidence to reject the null hypothesis, or say that we are rejecting the fact that there's no difference between these means. Now, being that this p-value is the very small value that is in this extreme end of the tail, another way to state that is if our p-value, which here it is here, this very small number, is smaller than the indicated alpha level, in our case here, 2.5%, then we would reject HO. When a test statistic falls in the critical region, it is more likely that this data is coming from a different group rather than being an extreme case. In our example, this t-value of 8.33, we can see it is much more likely that it is coming from this green population rather than being in an extreme case from this blue population. And this idea is fundamental to all of these statistical tests. Now, let's get ready to run Excel. We will need to use the analysis toolpack. And I'm going to just show you a set of instructions for how to ensure that that is set up on your Excel for a PC. It's much simpler on a Mac. It's almost automatic. So, on your PC, if you open up Excel, from the main file, click into the file and go down to Options. Next, click into Add-ins, and this window will appear. You can click on Analysis Toolpack, but then click Go. Next, this pop-up comes up, and you have to ensure that Analysis Toolpack is checked, and then you click OK. Now, your Excel data ribbon should have the data analysis pane ready to use. In order to find the ANOVA test in your Excel, you would click into the data ribbon, click over to the data analysis pane, and then you can select which particular test that you wanted to use. Now, let's open Excel. So, here's my Excel, and I already have it preloaded with the data from the diabetic children study. You can see that we have 25 observations right here. There are only two groups to compare here, the control group versus the one test group. Being that there are only two groups, that means that we can use the t-test. In order to perform a t-test, it's quite simple. All you need to do is click into a cell, enter equals, and start typing t-test. If I type t-test, we see that there are 4 fields that need to be filled in. Array 1, that's the data from dataset 1. Array 2, the number of tails, and then the type of test that we want to perform. So array 1, I will grab this data here from the control dataset, and we see that we go from B2 to B26. Okay. Oop. And array 2, that is C2 to C26. The number of tails. Our example is a 2-tailed distribution. And then the type. We have 3 options: paired or 2 samples, equal variance and unequal variance. Paired would be if it was the same individual measured between 2 time points, say before or after a treatment. But that's not our case here. So we'll say 2 sample equal variance. As a general rule of thumb, we can look at the standard deviations. If one standard deviation was more than double the other, we would say it would be unequal variance. That's just a general rule of thumb. However, there are statistical tests that can be used, namely the F-test for equal variance, but we'll just keep this like this. Then, after we have those fields filled in, we press enter, and this returns the p-value. We can see that this p-value is a number that is extremely small, 3.5 times 10 to the negative 6 power. So that is a number that definitely falls in the extreme end of one of those tails. And more importantly, it is a value that is much smaller than our alpha level of significance. Therefore, we have enough evidence here to conclude that we can reject the null hypothesis. We can also now perform an ANOVA, even though we have 2 groups. So I'll show you how to do that now. In the Data tab, I'll go to Data Analysis, and here we have 3 choices for the ANOVA. In this case, we're going to do the single factor ANOVA. That means that there is a single independent variable. I'll click OK. And now we have to define the input range. Click on this here. The input, we can simply grab all of our data. Okay. And our data is grouped by columns. We are, in fact, including the labels in the first row, as we have here. Our alpha level is set to 0.05. And then we just define how we want to output the information. I'll put it into a new worksheet, and I'll say ANOVA diabetes. Okay. Here's our output table. Let's make this a little bit bigger. Looking at our output table up top here, we have summary statistics for the control group and the diabetic parent group, average and variance. But more importantly is the ANOVA output. Make that a little bit bigger. What I like to look at right away is this p-value. Between groups p-value, we can see that this 3.5 times 10 to the negative 6, that's the same p-value that we saw with the t-test. This is further evidence to conclude that these 2 data sets are in fact different. What I'd like to do now is to try another example. The example that I'll try next is coming from a pesticide study of river water. In this study, river water was spiked with pesticides to see if solid phase extraction columns could capture it and detect its presence. There are 2 aims in the study. One, to test the levels of this pesticide that can be seen in various bed weights of these solid phase extraction cartridges. And the second objective is to compare the different materials, the stationary phase materials, packed in these SPE columns. We have a couple different values here. The data for this is presented here. In this left column, here's the list of various pesticides that were used. In these vertical columns here, we see the different bed weights of these SPE columns that are packed. We have 30 milligram bed weight, 100 milligram bed weight. Oh, and this is all in the 1 ml size. And looking at 3 ml size, I have quite a few to choose from. With these 3 ml columns, I have 30 milligram bed weight, 50 milligram bed weight, 100 milligram bed weight, 250, and 500. Also, at the bottom, we have the average values of all the pesticides. So these would be the data points that I'll use for this first example. In my Excel spreadsheet right here, I've already copied in the data from the 3 ml columns. And we have 30 milligram bed weight, 50 milligram bed weight, 100, 250, and 500. I also copied in some of the data from that data set for some sham columns. Our null hypothesis states that there is no difference in pesticide retention between the different bed weights, and our alternative hypothesis states that there is a difference in pesticide retention between the different bed weights. So, looking here, we have 1, 2, 3, 4, 5 groups just of the bed weight plus some extra sham weights. So being that this is more than 2, we have to use an ANOVA. So let's set that up. Again, I will click the Data tab, click Data Analysis, Single Factor ANOVA, okay. And let's define where our data is coming from. First, let's just grab the data just for these different bed weights, okay. We're defined by columns, we have labels, 5%, and let's output it to a new sheet and say bed weight. Okay. Looking at this output table, we see our summary statistics for our various bed weight. And if I go to the output of the ANOVA table, our p-value is 0.5, or 50%. 50% is not less than 5%. This p-value is larger than our critical region. Therefore, this is not statistically significant. This is telling us that we do not have enough evidence to reject the null hypothesis. There does not seem to be a difference between these bed weights and how much pesticides are retained on them. Let's go back and now try it one more time, but let's include the sham data or the negative controls. So let me click Data, run another ANOVA, single factor ANOVA, okay. Grab the data, but now let's include the sham data. Okay, defined by columns, okay, 5% alpha level, and we'll output this to bed weight sham. All right, let's take a look here. We see we have our groups with our bed weights plus our shams. Looking at the p-value now, I see this p-value drop down to 2%. This is indicating to me that there does seem to be some statistical difference somewhere among this data. At this point, I don't know where it lies, but I know that it exists somewhere. In order to find out between which groups the difference lies, I would have to perform a post hoc test. Excel is limited in its capabilities for performing post hoc tests. So we would likely want to appeal to some other software package like SPSS or Python. For this example, I'm going to point us to a website, this website right here. This is a one-way ANOVA calculator, and it will automatically do a Tukey post hoc test. And the way that you use it is simply define how many groups we're doing. So we have 8 groups. We have our various bed weights plus our sham data that we put in there. So I, in advance, just copied my data into there. And then click this. Now we have some descriptive statistics. We have the output of our one-way ANOVA. Notice the p-value here is 2% from our one-way ANOVA. Actually, let's read it off. It's 0.0201. To quickly go back to Excel, 0.0201. Okay, so that matches. But we came here because we wanted to find out where the differences lie. Note that when we did this the first time, we saw that there was no difference between just the bed weights. The only differences that we found was only after we added the sham data. So if we go down below to the output of the Tukey post hoc, here's the Tukey results, and this is our pairwise analysis. Notice AB, AC, AD, insignificant, insignificant, insignificant. And now we get down here, we have a few significant tests. This tells us that between group E and F, E and G, E and H, there are statistically significant differences. Okay, so if I go back to my Excel, here's the data. This would be group A, B, C, D, E, F, G, right? So it seems between this 500 milligram bed weight, we have statistical differences between this and each one of the shams. Okay. Let's try one more example. And this final example that I'd like to try would be to address the second aim in this study. This second aim in the study wanted to look at the material packed in the SPE cartridges and see if that has an effect. So I'm going to set up a 2-factor ANOVA. So we will test not only the packing material, this nanopack C packing material versus the C18 packing material, but we'll also test the bed weight. In this 2-factor ANOVA, there will be 2 independent variables, bed weight and packing material. With the 2-factor ANOVA, the null hypothesis takes 3 forms. That is, there's no difference between the first factor of the 2 groups. There's no difference in the second factor between the 2 groups. And then also there's no interaction effects between those 2 different groups. And then the alternative hypothesis says that there is some difference. To set up the 2-factor ANOVA, same way, go to Data, Data Analysis, and now we will go 2-factor with replication. With replication meaning that we're just taking more than one observation for each one of these groups. Define where our data is. There it is. That looks good. Rows per sample. I have 2 rows for each one of the samples, so those have to be equal. Our alpha level is set at 0.05, and let's say OK. All right. We have summary output for the one material, nanopack C. We have summary for the other group, C18, in each one of the bed weights that we tested. But now going to the output table, I see 2 statistically significant p-values. For the samples, meaning the material packed in the columns, the nanopack C versus the C18, there seems to be a p-value of 0.005. This value is smaller than 0.05, therefore this is statistically significant. Also, for the columns, and when they say columns here, they're referring to these columns, the bed weight. There's also a statistically significant effect here. There does not seem to be a statistically significant interaction effect. To recap, a t-test can be used to find statistical differences between 2 groups. For 3 groups or more, you need to use an analysis of variance, an ANOVA. The ANOVA uses the F distribution and the F-test statistic, which is a bit different from the t-test, but interpreting the results from a software application, they're similar. If you run an ANOVA and you find that the p-value is smaller than your set level, 5%, this tells you that there is statistically significant differences that exist in one or more of the groups, but it does not tell you which one, especially if you're running a single factor ANOVA. To find out which groups are different, you need to run a post hoc test. Some examples of post hoc tests. These are ranked from conservative to aggressive. The Bonferroni, the Schiff, Tukey, SNK, and Fisher. If you have large sample sizes, you could run some of these top tests, the Bonferroni, for example. If you have smaller sample sizes, you want to go to the bottom. The Tukey is right in the middle. Most literature papers that I read reference Tukey tests, and I think that strikes a nice balance that fits most situations. To recap on the differences between the factor design, a single factor design, that means that there's one independent variable and one dependent variable. In our example, the how does column bed weight, the independent variable, influence analyte retention, the dependent variable. Contrast that with the two-factor design, where we have 2 independent variables and 1 dependent variable. How does column bed weight and stationary phase influence analyte retention? And for the two-factor design, the null hypotheses have to be more inclusive. You have to test whether there's a difference between groups for the first factor, difference in the groups between the second factor, and also interaction effects. This is the URL of that web-based application that we used to run the one-way ANOVA with the Tukey test. And also, so far we've only been talking about data that's normally distributed and the tests that are used for normally distributed data. However, if you're dealing with non-parametric data or data that is skewed, like pictured here, you could use something like the Kruskal-Wallis test. That is the non-parametric version of the ANOVA. To follow up the Kruskal-Wallis test, you typically use, say, the Dunn post hoc test or one of these other that I have listed here. And that concludes this presentation. Thank you.